Deep learning is a subset of machine learning that uses artificial neural networks, ANNs, to model and solve complex problems. It is inspired by the structure and function of the human brain and excels in handling unstructured data like images, audio, and text. Deep learning is the driving force behind many state-of-the-art technologies such as image recognition, natural language processing, and autonomous vehicles. Structure of a neural network input layer receives the input data, with each neuron representing a feature. Hidden layers perform computations using weights, biases, and activation functions to transform inputs into intermediate representations. Output layer produces predictions or decisions based on the processed data. Key components, weights and biases, parameters adjusted during training to minimize error. Activation functions introduce nonlinearity, enabling the network to learn complex patterns. Common functions, ReLU, sigmoid, tanh, softmax. Loss function measures the difference between predicted and actual values. Examples, mean squared error, MSE, for regression tasks. Cross entropy, loss for classification tasks. Optimization algorithms minimize the loss function by updating weights and biases. Examples, gradient descent, stochastic gradient descent, SGD, atom optimizer. Deep learning architectures. 1. Feed-forward neural networks, FNNs. Simplest form of neural networks where data flows in one direction. Commonly used for basic tasks like regression and simple classification. 2. Convolutional neural networks, CNNs, specialized for processing grid-like data such as images. Key components, convolution layers, detect patterns using filters. Pooling layers, reduce spatial dimensions to retain essential features. Fully connected layers, combine features for final predictions. Applications, image recognition, object detection, and video processing. 3. Recurrent neural networks, RNNs, designed for sequential data, with feedback loops allowing information to persist. Variants, long short-term memory, LSTM, handles long-term dependencies. Gated recurrent units, GRU, simplified version of LSTMs. Applications, natural language processing, NLP, time series forecasting, and speech recognition. 4. Generative adversarial networks, GANs, composed of two networks. Generator, creates synthetic data. Discriminator, distinguishes between real and synthetic data. Applications, image synthesis, style transfer, and data augmentation. 5. Transformer models. Utilize self-attention mechanisms for parallel processing of sequential data. Revolutionized NLP with architectures like BERT, GPT, and Transformer XL. Applications, machine translation, sentiment analysis, and text generation. Which are the main challenges in deep learning overfitting? The model performs well on training data, but poorly on new data. Solutions, regularization techniques, L1, L2 penalties. Dropout, randomly deactivate neurons during training. Early stopping, halt training when validation error increases. Vanishing, exploding gradients. Gradients become too small or too large, affecting learning. Solutions, use activation functions like ReLU. Employ techniques like batch normalization. Computational complexity. Training deep networks requires significant computational resources. Solutions, use GPUs or TPUs. Optimize code with libraries like TensorFlow and PyTorch. Data requirements. Deep learning models require large datasets to perform well. Solutions, data augmentation. Transfer learning with pre-trained models. Deep learning leverages neural networks to solve complex problems, particularly with unstructured data. Various architectures like CNNs, RNNs, GANs, and transformers cater to different data types and applications. Challenges such as overfitting, data requirements, and computational complexity can be mitigated with best practices and advanced techniques. Deep learning is transforming industries, from healthcare to finance, offering innovative solutions to pressing challenges.